Radical and rational functions review. Starting off with radical function review. Graph and analyze radical functions, limited to functions involving one radical, so you can't do two. And sketch the graph of the function y equals square root x using a table of values and state the domain and range. So we're going to sketch the graph of y equals square root x by creating a table. So if you actually look in your table at like -1, you have an error because you can't take the square root of a negative number. At 0, you have 0. At 1, you have 1. At 2, you have 1.4142. But I like picking whole numbers, so I'm going to pick 4 and 2. And skip to 9 and 3 because the square root of 9 is 3. And I'm going to plot it. 0, 0, 1, 1, 2 and 1.4, 4 and 2, 9 and 3. Okay, and then sketch the graph. So that's your basic square root x graph if it hasn't been transformed to the left, right, up or down. Key thing to remember about this is that it starts at 0, 0. So the only thing that can move this point right here, this 0, 0 point, is a horizontal translation or a vertical translation. Anything else, stretches and reflections, aren't going to move it because stretches and reflections, you multiply. So if I take 0 and I multiply it by -2, and that would be a horizontal stretch by -2 and reflection on the y-axis, 0 times -2 is still 0. The only thing that's going to move this point are vertical and horizontal translations. So if that point is moved, you have a vertical and or a horizontal translation. Sketch the graph of the function y minus k equals a square root b x minus h by applying transformations to the graph of the function y equals x and state the domain and range. So we have create a radical equation that has a domain of x is less than 2. Now, your basic function up here has a domain of x such that x is greater than or equal to 0, XER. So the only way you're going to get less than is if we have a reflection in the y-axis. We'll get a less than or equal to sign. Our range is y such that y is greater than or equal to 0, YER. And the only way you'd get a less than is if you have a reflection in the x-axis. Then you get a less than or equal to. And this little value here is our horizontal translation always, and this little value here is our vertical translation. They just happen to not be translated at all. So let's go back to these graphs. So my x is less than. So if my x is less than 2, I know I have a reflection in the y-axis. And if it's less than 2, I know I have a horizontal translation to right. Because my stretches do not affect my domain. Because if I multiply by a positive number, it's not going to change anything. Now this one is greater than. So I don't have no reflection. I don't have a reflection. And my vertical translation is 5 up. So when I go to write my equation, I'm going to get y, I'll put it in that form in a second, y equals a. My a doesn't change, so it would just be a 1. I don't have a vertical stretch or a reflection, so I don't even have to write the 1, but I'm going to. And then my b is just -1 because I don't have a stretch. I could have a stretch, I guess, but in this case, it doesn't say anything about that. And then I have x minus 2. From the domain and range, you can't tell if there's stretches. And then it's 5 up, so at the back I have plus 5. If I wanted in this form where it's y minus k, I would have y minus 5 equals the square root of negative x minus 2. In order to sketch the graph of y plus 7 equals 3, square root 2x plus 6, state the transformations that would need to be applied to the graph of y equals square root x. So I'm going to move that 7 over first. Y equals 3 square root 2, and I always make sure this is in brackets. If there isn't a bracket in here, I have to remember to take the horizontal stretch out, but I don't have to in this case because it's already been taken out, minus 7. So in front of the radical, I have a 3. So I have a vertical stretch by a factor of 3. And remember, we can't write VS and BAFO. If we actually wrote this out on a test, we have to assume that no one knows what that stands for but you. So you have to write vertical stretch by a factor of. You have to write the whole thing out. 3 about the x-axis. We have the 2 here. So that's a horizontal stretch by a factor of, and this horizontal stretch always flips. It doesn't matter what unit we're in, always flips. A half about the y-axis. We have a vertical translation 7 down. And we'd have to write vertical translation again. And horizontal translation, we can't write h of t, we'd have to write horizontal translation, 6 left. So we want to sketch the graph using those transformations. So we'd have to plot our original. Our original we know is at 0, 0, 1, 1, 4, 2, 9, and 3. So our original points on y equals square root x are 0, 0, 1, 1, 4, 2, 9, 3. Why are they helpful? Because if we're moving points, we use mapping. Okay? So our xy is going to become anything inside here affects my x variable. Anything here and back here, or in this case over here, affects my y. So my x's are going to be multiplied by a half x, and then I'm going to subtract 6 because I'm moving 6 left. And my y's I'm going to multiply by 3y, and then I'm going to subtract 7. And I'm just going to now apply them to all my points. So I'm going to 7, 0, 0 for my xy. So I'm going to get 1 half times 0 minus 6, comma 3 times 0 minus 7. And that 0, 0 point has been moved to negative 6 and negative 7, which makes sense because the only thing that can move that point, I told you, was horizontal and vertical translation. It doesn't matter that there were stretches at all. It wouldn't matter if there was reflections. That's not going to change it. The only thing that moves this 0, 0 is horizontal and vertical translation. So I'm at negative 6 and negative 7. So about here. Then I do my next point, plugging it into mapping. 1 half times 1 minus 6, and then 3 times 1 minus 7. So 1 half times 1 is a half minus 6 is negative 5.5. And then 3 minus 7 is negative 4. So I'm at negative 5.5 and negative 4. And 4 and 2. Going to get a half times 4 minus 6, comma 3 times 2 minus 7. So a half times 4 is 2 minus 6 is negative 4. And then 6 minus 7 is negative 1. So I'm at negative 4 and 1, negative 1. And then 9, 3 is going to become a half of 9, which is 4.5, minus 6. And then 3 times 3 minus 7. So I'm going to get 4.5 minus 6, which is negative 1.5, comma 9 minus 7, which is 2. So negative 1.5 and 2. And there's my new graph. So both of my domain and range would be greater than or equal to, because neither of them had reflections, right? And they're going to be greater than or equal to my horizontal translation, which was 6 to the left, and my vertical translation, which was 7 up, or 7 down. So my domain is going to be greater than x, such that x is greater than or equal to my horizontal translation, which is negative 6. And my range is going to be greater than or equal to, because there wasn't a reflection, negative 7, which is my vertical translation. It's the only thing that moves at 0, 0, and this only happens with radical graphs. So now we have the graph of y equals square root x has been reflected in the x-axis. So that goes with the y. Stretched horizontally by a factor of 4, so when I put that back in, I'm going to put in a quarter. Translated to right, when I put that back in, I'm going to do x minus 2. 5 down, I'm going to put that in as a negative 5. So I'm going to get y equals, and I don't have to apply any of this to any of the other stuff because this graph hasn't been moved at all. It's just square root x. So I'm going to get negative, sorry, not negative, reflecting the x-axis. So I'm going to get square root, yeah, x-axis. So negative square root 1 quarter, because the horizontal stretch by factor 4, x minus 2, because it's 2 to the right, minus 5. Now, normally you would have to apply your stretch and reflections first. In this case, we don't have to because the original didn't have any. But had the original actually had some vertical translations, we'd have to apply the negative 1 to that as well before we translated. Sketch the graph of the function y equals square root f of x given the graph of y equals f of x and explain the strategies used. So when you look at radical graphs, they have invariant points when y equals 0 and y equals 1 when you're looking at a basic function graph and then the square root of that function. Why would that be? Because if I square root, in order to get from this graph to this graph, I take all the y's of this graph over here and I square root them to get the new y's in my radical graph. Well, when I square root 0, which is one of the y's, I get 0. And when I square root 1, I get 1. So they don't change. And if they do not change, they're invariant. So first off, we're going to sketch the original, which is a line. It has a y-intercept at positive 1. And then up 1. I always have to rise before I run, or I'm not going anywhere. So I rise up 1 and over 2. And they're both positive, so up 1 and right 2. Up 1, right 2. Up 1, right 2. Up 1, right 2. Hard to see. And I can go the opposite. Down 1, left 2. Down 1, left 2, etc. Connect those, and I have my original. Oops. Now, what I do to get my new one is I square root all the y's and keep the x's. Well, if I square root any of the y's down here, they're going to go away because you can't square root a negative. This one is negative 2 and 0, so it's going to become negative 2 and square root of 0, which is still 0. So it's invariant. And so I have an invariant. And you could solve these algebraically by putting 0 in for y and 1 in for y into the original. I have an invariant at negative 2, 0. And at 0, 1. Because it's going to be 0 and square root of 1, which is just 0 and 1. So I have 2 points. The values of y in between 0 and 1 are decimals. And when you take the square root of a decimal between 0 and 1, it gets bigger. So if I take the square root of 5, it ends up going to 0.707 or something like that. I'm going to plot it above. So I get this little curve. And then if I take the square root of 4, it's going to drop down to 2. So I get a curve down here. And you square root all of them. And you're going to get this radical graph. It's going to grow a little bit at a time. So how are the domain and the two of the two functions related? Well, where they both exist, where the two graphs exist, will be where the domain is. So in this case, the radical graph only starts when y is positive or 0. So in this case, the domain is going to be x such that x is greater than or equal to negative 2, because before that, I have negative numbers. And it can equal negative 2, because at negative 2, y equals 0, and I can take the square root of 0. Compare the domain and range of the function of y equals f of x to the domain and range of the function of y equals f of x and explain why the domains and ranges may differ. So this is the original f of x function, and they want the square root of that function. So I'm going to go keep all the x's and square root my y's. So here I have negative 10 and 4. It's now going to become negative 10 and 2 because it's going to be negative 10 in the square root of 4, which is 2. Where I have 1s, they're going to stay the same. where y equals 1 and where y equals 0, they're going to stay the same. Wherever I have negatives, that no longer exists. So I'm crossing it out, but it wouldn't actually be there. So on the radical function, this is gone. Now 0.5 is going to move up to 0.7 at the same x. 0.5 is going to move up to 0.7 at the same x. And then I can follow 4 over. And this is where 4 is. So that looks like possibly 6 and 4. It's now going to be 6 and 2 because the square root of 4. Where I have 9 is, it looks like 8 and 9. It's now going to be 8 and the square root of 9. So I drop it down to 8 and 3. So I get a graph that's going like this. A graph that's going like this. So wherever the domain of the original is actually below 0, so the range is below 0, it's going to go away. And we're going to only be left with the x's. So we're going to have x such that x is less than or equal to, and we need to figure those ones out. X is less than or equal to this value here. Or x is greater than or equal to this value here. XCR. We would need more information as to what our x-intercepts are, specifically in this case, so we couldn't find them. What we'd have to do is figure out the equation of the quadratic and then find the x-intercepts from there. But usually on the diploma, they give you more information. Explain the strategy you use to sketch the graph of y equals f of x. You keep the x's, the original x's, x values, and square root their y's. Draw a new point. The domain I stated above, but I'd have to guess as to what those numbers are. The range in this case is easy. It would be y such that y is greater than or equal to 0. And it's always that if some of your graph is below the x-axis. If some of your original graph is below the x-axis, your range will always be y is greater than or equal to 0. Oh, sorry. This is the domain of f of x. The domain and range of f of x, the domain would be XER, and the range would be greater than -4. That's the minimum. The radical I explained above for the domain, the range would be greater than or equal to 0. It says explain why the domain and range are different. Because you cannot take the square root of a negative function. Of a negative, I guess, y value, sorry. So on the radical graph, all those corresponding x values that have negative y values will go away. So state the coordinates of any invariant points between f of x equals 1/2 x minus 3 is transformed to this. To do it algebraically, the invariant points when you take the radical happen when y equals 0, because the square root of 0 is still 0, and when y equals 1. So you could take either the original or the original under the radical sign and set y equal to 0 and solve, because you're going to get the same points between the two because they're invariant. So I'm going to just use the original and not the radical one always, just because it's one less step to solve. So I'm going to get 0 equals 1/2 x minus 3, add my 3. I get 3 equals 1/2 x, multiply by 2, and x equals 6. So my one invariant point is at 6 and 0. Remember, they're invariant points. So in order to have an invariant point, you need to have a coordinate, which means you need to have an x and a y. Now, when y equals 1, I'll plug it into this equation for y. So I'm going to get 1 equals 1/2 x minus 3. Add 3 to both sides. And I get 4 equals 1/2 x multiplied by 2. X equals 8. You need to know how to do this algebraically. Yes, you could go into your calculator and plug into y2 0 or plug into y2 1 and find out where they cross. But you need to be able to do this algebraically. So 8 and 1 is the other invariant point. Now, if your original was a quadratic, you might get 2 invariant points, or 1, or none if they're all completely it. So if your original was a quadratic, here you would get 1, 2, 3, 4 at 0 and 1. If your quadratic was like this, you may only get 1, where y equals 1. Not drawn the best. And then if your entire graph is above 0 and 1, you may get no invariant points. Describe the relationship between the roots of radicals and the x-intercepts of the graph. Roots are the x-intercept. So to determine the x-intercept, whenever we hear x-intercept, we should always think for x-intercept, y equals 0, and solve. And they went to the nearest hundredth. So in this case, we could type it into our calculator and find the x-intercept, but we're going to actually, so you'd go y1 is the function, and then second trace zeros, and then left bound, right bound, and get your x-intercept. But I'm also going to check it by solving it properly. So 0 equals -2 square root x plus 4 plus 3. Subtract the 3. Now, because moving the 2 over wouldn't make it very nice, it wouldn't divide evenly, I'm going to square it. I'm going to get 9 equals, and I have to remember to square this and this. It's not foiling because I don't have a plus or minus sign here. I have a multiplication between these two. So I'm just going to square the -2 and get 4. And then I'm going to square the square root sign, so it's going to go away. So I'm going to get 9 equals 4x plus 16. Subtract 16. 7 equals 4x. Divide by 4. X equals 7 over 4. So my answer would be 7 over 4 and 0. And to the nearest hundredth, I would have to go 7 divided by 4, which would be 1.75. Yeah, because it would be 1 3/4. Determine graphically an approximate solution of the rational equation. Sketch it below. So in this case, I won't sketch it, but I will show you in my calculator. Just writing it down so I can continue my calculator. Moving out of this screen. So my y equals, take out my trig. Okay, so in this side, I go square root 17x minus 4. I'm going to put it exactly how it is. Minus 2. And then in y2, I'm going to put 7. Let me go zoom 6 and see if I can see it. There it is. So I'm going to find out where they intersect. And I can do this whenever I have an equation with one variable and an equal sign. Second trace 5. Enter, enter, enter. I need to get onto a curve here. There we go. Enter, enter, enter. And it's at 5, 7. I don't care about the y. That's where the right-hand side is. That's where y2 is. It's at 7. I care about the x. So this intersects at 5. So that's showing you how to do it with your calculator. So our intersection point, or our solution, is at 5, 0. Or x equals 5. And we can check it, but we've kind of checked it with our calculator already. Explain the strategy you used. I used my calculator. Y1, I made B this side, and Y2 this side. And then I followed that. and then rationals, which I will deal with in another video.